Moving on to how to prevent these routing loops from happening in the first place. Well, the first method deployed by distance vector routing protocol is having maximum hop counts for packets or routing updates. So as you saw when that loop was happening and the counting to infinity problem was happening, RIP deploys a maximum hop count of 15. So a routing update can go a maximum of 15 router hops. The 16th router kills the packet. So when the maximum hop count is reached, the packet is killed. So it doesn't loop around the network endlessly. The second one is split horizon. Split horizon basically says, let's say this is router 1, and we have router 2, and again, network 10. Network 10 is available to router 1 through router 2. Router 2 is sending updates about network 10 going out serial 00 interface, S00 interface. So the rule of split horizon basically says, if I send an update about a network outbound on an interface, I will not accept an inbound update about the same network coming in on that interface. So if router 2 sends an update about network 10 out of the serial 00 interface, router 2 will not accept an update about network 10 coming in on the same interface. And it makes sense. The only way network 10 would arrive on serial 00 on router 2's serial 00 interface is if there was a loop here somewhere downstream and the update looped around is now on its way back. So the rule of split horizon says, once again, if I send an outbound update out an interface about a certain network, I am not going to accept an update inbound on the same interface about the same network. Moving on, the rule of route poisoning. The rule of route poisoning basically says that you advertise a down route with an infinite metric. So for RIP, 16 is infinite. The maximum hop count for route information protocol, or RIP, is set to 15. So if this network for any reason goes down, this link fails, router 2 will immediately send an update to router 1 telling router 1 that network 10 now has a hop count of 16, or an infinite hop count. And you can never get to an infinitely far away destination, so router 1 won't even bother trying to route to network 10. The fourth one is route invalid timer. Let's say there is another router here on an Ethernet link connecting router 1, which is router 3. And once again, network 10 is available to router 1 and router 3 through router 2. Let's say this interface, which is serial 00 again on router 1, has a malfunction. And router 1 stops sending updates to router 3 about network 10. Well, router 3 will wait the length of the route invalid timer, which for RIP is 180 seconds, and then if it does not hear about network 10 in 180 seconds, router 3 will mark that network as possibly down and stop routing to it. So once again, the route invalid timer is the length of time a router will wait to hear a routing update from an upstream router before declaring that route to be possibly down and stopping any routing towards it. The next one is hold down timer. Now, when the invalid timer expires, the hold down timer is started. The hold down timer for RIP is 180 seconds. So when the invalid timer expires and the route is considered possibly down, the hold down timer starts. A route, when it's put in hold down, when a router puts a route in hold down, it will not accept any updates about that route for that length of time, with RIP it being 180 seconds. Why is this so? Well, back in the olden days, router interfaces, when they went down, and when they came back up, they used to flap. They used to go down, come up, go down, come up, go down, come up before stabilizing. So this was a mechanism for the router not to continually add and delete that route from the routing table as the upstream interface came up and down, came up and went back down. So router 3 in that case would say, okay, hold on. This network was down for a while. Now it's back up, but I'm not going to accept any new updates for this network for the length of the hold down timer because I'm not sure whether you're stable yet. Have you come up and you decide to stay up for a period of 180 seconds, then I will start accepting updates about this network. Because I don't want to constantly add network 10 and then take network 10 away from my routing table. Because when I'm doing that, I'm not actually routing. And packets could back up. So when the route invalid timer expires, which is 180 seconds, the hold down timer is started, which is another 180 seconds. Now, while the route for network 10 is in hold down, router 3 will send a poisoned update upstream back to router 1 saying, hey, I haven't heard about network 10 for 180 seconds. I am putting this route in hold down and I'm not accepting any updates about network 10 for a period of 180 seconds. And while in hold down, I'm also going to tell router 1, hey, get rid of this route from your routing table because I haven't heard about it for 180 seconds and it's probably down. That process is called poison reverse. So basically, router 3 will send an update about network 10 back to router 1 with a hop count of 16, which in RIP is infinite. So advertising a route back upstream with advertising a poisoned route back upstream towards the origin of the network with an infinite metric or an unreachable metric is called route poisoning. The last one is route flush timer. This is the time at which the route is completely removed from the IP routing table. For RIP, that is 120 seconds. Now, one last note on RIP. Right now, we are doing RIP version 1, or simply called RIP, or Route Information Protocol. RIP version 1 is classful, which means it only understands class A, class B, and class C addressing. Also, that means that subnet mask information is not carried within the routing update. Okay? You look at the first octet and you know it's class A. You look at the first octet, you know it's class B or class C. Okay? And you assume a mask of either /8, /16, or /24. This concludes our Route Information Protocol lecture, and now we'll get to the lab.